There, can everyone hear me now? Or, okay, better. So the second lecture, we're going to do some explicit modeling techniques, starting with some simple regression and then moving up to hierarchical modeling. And I'll show some stand code of kind of the simple example models, as well as trying to emphasize a lot of things that can go wrong and some of the things that you want to do to make sure everything's robust, right? Because one of the things that we're trying to emphasize in Stan, it's not just about getting an answer quickly, it's about getting the right answer as quickly as possible. Oh, good? Excellent. Okay. So I want to begin talking about Hamiltonian Monte Carlo by trying to emphasize what I mean by scalable Bayesian inference, because this is a bit of a loaded... Oh, sorry. Also, I tend to talk a little quickly, so I'm going to try to talk as slowly as possible. If at any time I start getting a little bit too quickly, for anyone, please don't hesitate to raise a hand or even shout out to let me know to kind of slow down again. We've got plenty of time. There's no need for me to go as quickly as possible. And similarly, if there's any questions at all, anytime during the talk, please raise your hand. I'm more than happy to address it when it's appropriate in the material. All right, so as I was saying, I want to start by defining what I mean by scalable. In this world of big data, scalability oftentimes has many definitions depending on who you talk to. So I want to make that very, very clear what I mean by that and the particular challenges that arise for Bayesian inference when we're in this scaling regime. That is then going to motivate Hamiltonian Monte Carlo, and I'll spend a good bit of time talking about how Hamiltonian Monte Carlo works at an intuitive level, and then some of the ways we tune it to optimize its performance in tools like Stan. So to begin everything off, I'm going to start with an example, and this comes from some research I did a few years ago with some astrophysicists. And we were studying these things called supernova, right? So supernova are these exploding stars in the sky. Right? So it's a star, it kind of gets a little bit too old, and the whole thing just goes crazy and explodes. And it has this very, very characteristic light curve. So if you're looking out in the sky at one of these stars, you'll first see this very, very rapid rise in light, this kind of plateau, and then this slow decay. So there's these three distinct phases. And the better you can measure this light curve, the better you can understand what happened to the supernova, right? And clearly it's going to be useful for physics. But more importantly, the more of these supernovae that you can measure accurately, the better you can constrain things like how big the universe is, how old the universe is. Right? These are really, really important for us to understand how the universe works. So it's really critical that we measure not just one of these supernovae really well, but as many as possible. Right? The more supernovae we have, the better we can constrain how old the universe is, how large the universe is, etc. The challenge is that these supernovae are rare, right? So this is your classic big data problem. We need lots and lots of data to have a reasonable number of supernovae to do our analysis. And so the way we try to solve this in modern astrophysics is with what's called a survey. So you take a telescope and you just have it scan across the sky over and over and over again, right? You're essentially taking a movie of some big part of the sky. And if you do that long enough, you collect terabytes, if not exabytes of data, and then if you sift through that enough, you'll eventually find a good number of supernova candidates, right? The problem with all of that is that the supernova candidates you get aren't really clean, right? Because it's much more likely that you're just going to capture the end of an explosion rather than the whole thing, right? You're scanning through the sky. You're not watching one part of the sky very particularly. So you're going to have a lot of these supernova candidates, but there's going to be a lot of cutoff measurements, right? You might measure the end. You might measure the beginning. You might measure somewhere in the middle, right? And this is a real classic problem with big data. We have lots of data, but it's corrupted, right? It has all of this rich structure in it. And if you don't take that structure into account, you're only going to get so much out of the data. And so when we're talking about building a statistical analysis, we have to consider not just the size of the data, but also the complexity of the model that we need to capture the richness of that data, right? We need to capture that structure. And this means that when we talk about scaling our models, right, we can scale multiple ways because this is a two-dimensional plane. You can imagine scaling to a really, really big data set that's really simple. Right? It's just IID data. You can just fit it with one Gaussian, for example. Right? A lot of machine learning is focused on that regime. You could also imagine having a model that's really complex with very little data. Right? So kind of a physical science model where the model is getting more and more complex, but the data isn't really changing that much. Or you can imagine having a model whose complexity grows with the size of the data. Right? The more data you collect, the more parameters you need. That's becoming very, very common in a lot of modern statistics. Right? So there's multiple ways that we could have to, problems in which we'd have to deal. Now, there is a really nice decomposition of this space, kind of a binary decomposition, that I think really nicely demonstrates the main thrusts in a lot of academic work these days. And this is the so-called tall data, wide data breakdown. So tall data is characterized by being in this corner of space. We have lots and lots of data relative to a pretty simple model. In other words, the data are really, really informative. Right? So we have all of these parameters, but we can confine them to a really small neighborhood. Everything looks Gaussian. In fact, we have so much data we can throw some of it away, and things still work really well. So this is the area that you'll see a lot of machine learning focused in, where you have things like subsampling algorithms, where you kind of throw data away every now and then and still hope that you're going to do okay. And if you have really clean data like that, then those methods can work really well. But on the other side of the space, things are a little bit more challenging. This is the wide data regime. And in the wide data regime, you might have lots of data, but you're always going to have more model complexity than you can than the data, right? So there's always not enough information to really constrain all of your parameters down to reasonable values. And so the wide data regime is really characterized by having lots of uncertainty, and that uncertainty is really, really complex. Right? So it's really hard to quantify all of the parameters that are consistent with the data. And the unfortunate reality is that most big data applications are actually in the wide data regime. Right? Because we're not just collecting the data of the same process over and over and over again. Right? Time's varying. The individuals you're looking at are varying. There's all of these systematic effects, selection biases, observation biases, right? And if you don't take those into account, you're going to get really biased inferences. So you might start off with a simple model, but as you get deeper and deeper and you try to make more and more precise inferences, you're going to have to eventually deal with the wide data regime. And so that's what I'm interested in. Me and a lot of my colleagues, we're trying to build tools that facilitate analyses in this really, really challenging regime. We're going to have really complex models and really complex data. Now, the particular statistical perspective I'm going to be assuming here is Bayesian inference. And Bayesian inference is particularly suited to these wide data analyses because it gives us another way of adding information. Right? So any Bayesian analysis is going to begin with two steps. The first is choosing a likelihood. This is a generative model of the data, and you can really think about it as a story, right? How did I generate the data? And this is where you can incorporate a lot of those systematic effects. Right? This is where you can include selection biases, observation biases. You treat it as part of the measurement process. So this is going to be some big complex model that's really hard to fit, but then we're going to add to that a prior. And what the prior does is it regularizes the system based on information that we have at hand outside of the measurement. And this is really nice because it gives us a mathematically self-consistent way of adding more information. Right? If wide data analyses are characterized by not having enough information, anything we can add is going to help. So when we put these together, the prior tells us everything we knew about our system before the measurement. The likelihood tells us what we learned from the measurement. And so their product gives us the posterior distribution that encodes everything we know about the system after the measurement, right? It really quantifies all of our information after we've collected the data. Now, there's a very, very important consequence to this. If all of our information is encoded in the posterior distribution, then any kind of statistical question we ask has to be answered by some manipulation of the posterior. And there's only one thing that you can do to a posterior in a mathematically well-posed way, and that is to compute expectations. So when you're talking about statistics, every calculation that you do always resorts to some kind of integral. Right? This is a really, really important thing that oftentimes gets overlooked. There's a lot of approximations out there, but all those approximations have to reduce to computing an integral. So at this point, we're going to decouple from Bayesian inference and just focus on the challenge of computing expectations with respect to some target distribution pi. Right? So I'm not computing an expectation with respect to the prior here. This is just some arbitrary distribution. If we're doing a Bayesian analysis, it would be the posterior, but it could be something else for another analysis. So we do have this really, really nice decoupling in Bayesian inference, right? There's the modeling step where you model your prior and your likelihood, and then there's this computational step where we compute expectations. Really, really lovely conceptually. In practice, of course, these are both really hard. Right? Modeling is really hard, and we'll talk a little bit about that in the next lecture. But computation is also really, really hard. And that's because these integrals are really challenging to compute in high dimensions. Right? And high-dimensional parameter spaces are one of the characteristic properties of wide data analyses. So let's explore a little bit as to why that is. Right? Why are integrals hard? Well, let's consider what we'd have to do to calculate these. We can't do it analytically, right? Because these are going to be way too complex. So we're going to have to rely on some kind of numerical approximation. And to compute any kind of numerical approximation to an expectation, we have to identify where to focus our computation. Right? Where are we going to actually compute that integrand? Where are we going to compute the density? Where are we going to compute that function in parameter space? We can't just do it everywhere because we don't have enough computational resources. So we have to focus and identify where are we getting the most contributions to these expectations. Right? So what can factor into that? Well, certainly the function we're taking an expectation with respect to can change where which parameters are most important. Unfortunately, in most cases, we want to compute lots of expectations with respect to lots of different functions. So we don't want to over-tune to a given function. Right? So let's ignore that for now, and let's focus on the other contributions. The next obvious thing is the density itself, right? So our target density, in the Bayesian case, or posterior density. We want to try to identify where the density is large, right? Because if the density is large, the integrand is going to be large, and nominally the expectation would be large. Seems reasonable. Unfortunately, it's a little bit more complicated than that. Because when we're doing an integral, we're not just looking at that density, we also have to consider the volume over which we're integrating that density. And so sure, the density is large around the mode, but there's not that much volume there. Right? There's a lot more space out in the tails of the distribution. And so even though the density might be lower out there, the contribution to the integral can be a lot larger, just because there's more space over which we're integrating. And this gets worse and worse as we go to high dimensions. Right? In high dimensions, there's lots of corners, and so there's just more and more volume away from the mode than there is close to the mode. So the way you want to think about this is imagine over there at q equals 0, we have the mode, and the tail is over at large q, we're moving away from the mode. The density is going to fall off exponentially quickly. Right? Just imagine that's the Gaussian density. It's large at the mode, falls off really, really quickly. But the volume increases exponentially fast. Right? And this exponential growth actually gets exponentially faster as you go into higher and higher dimensions. And so what happens is we have these two competing forces. Right? The volume wants to focus us to large q. The density wants to focus us towards the mode. And the probability mass, the product of those two things, the thing that's actually contributing to the expectation, that's going to balance out in the middle. Right? And so this region where all of the probability mass concentrates is what we call the typical set. Right? So we're not looking at some mode in the center. We really want to be looking at this surface around the mode. Right? So the cartoon I'm going to use is going to be this. So just imagine some high-dimensional space, and all of our probability is concentrating on some weird surface that surrounds the mode. And this is the challenge, right? Because we don't have a lot of analytical guidance as to where the typical set will be. So we need some way of trying to find and then explore the typical set automatically, right? Without our being able to guide it. And that's really, really, really hard. So a lot of approximation techniques will try to approximate this, try to simplify that into some form where we can find where the typical set is. But that can really limit what we're trying to do. Fortunately, we do have a really, really nice way of automatically finding and exploring typical sets like this. And that is with a Markov chain. So a Markov chain is generated by this Markov transition operator tau. And you really kind of want to think about it as a random function. Right? So if we're at some point q prime, tau tells us the distribution of points at which we can jump to. We apply it, we randomly jump to some new point, and then we get a new distribution of points. right? You repeat this process over and over again, and that gives you a chain, a Markov chain, just a series of states that have been generated in this conditional fashion. Now, by itself, this isn't all that useful. It's just a random set of states. However, if we can engineer the Markov transition to preserve our target distribution, right? If we can engineer it to satisfy this property, then something pretty magical happens. If we satisfy this property, then the Markov transition is much more likely to jump us towards the typical set than away from it, right? It's literally attracted to probability. And so if we have this property and we keep applying the transition over and over again, it doesn't matter where we started. We'll eventually drift into the typical set and then start exploring that surface. Right? So graphically, it'll look something like this. We have our cartoon of the typical set. We're going to start somewhere off the page because in high dimensions, every point is really far away from the typical set. It's one of these weird properties of high-dimensional spaces. But it doesn't matter how far away we are. We just keep running the Markov chain, we drift in, and we start moving across the surface. Right? And if we run long enough, then the Markov chain will eventually distribute across the entirety of the typical set. And once it's done that, well, now we have a really nice quantification of where all of our probability is. Right? The Markov chain tells us where we should be evaluating our function. And so if we want to compute the expectation of some function f, any function f, all we have to do is average it over the history of the Markov chain. And this gives us what's called a Markov chain Monte Carlo estimator. What's particularly nice is that if we run the Markov chain long enough, we'll always converge to the true expectation. Right? We'll always get the right answer, provided we can run infinitely long. Now, this is one of these really lovely theoretical results that has little application in practice, because we don't have infinite computational resources. Right? We can't take n to infinity. We're always going to be limited to some finite n. And so what really matters for the efficacy of MCMC is how well we can do in some finite time. Right? How quickly are we converging to the true expectation? And unfortunately, this leaves us open to some pretty serious problems. So, the ideal case looks something like this, but imagine instead that our Markov transition was just a small little perturbation, right? We're generating these states by just moving our initial point in a small little way. Well, in that case, it's going to take millions, if not billions, of transitions to move across this very expansive surface, right? It's going to take many, many, many transitions. And if those transitions are expensive, which they'll typically be in the wide data regime where we have lots of parameters and lots of data, right? The calculations are expensive. Well, we're going to very rapidly exhaust our computational resources long before we get this complete exploration, right? It's much more likely that we get this partial exploration because that's all we can afford with computers that we have. But very clearly, if we only have partial exploration, we're going to get biased estimators. Right? We're missing a ton of probability. And this is unfortunately the circumstance of a lot of MCMC algorithms. So as an example, let's consider random walk metropolis. Right? This is literally the first metropolis algorithm, and still today one of the most popular. Right? If you take any kind of statistics class, this will be the first thing you learn when it comes to MCMC. And one of the reasons people like it is that it's really simple. You can always generate a valid Markov transition in just 2 steps. The first step is to add some noise to our initial point. Right? It's going to be typically isotropic Gaussian noise. And then that creates what's called a proposal. And then we accept or reject that proposal based on where we jump. If we jump closer to the mode, then we'll accept it. If we jump away from the mode, then we'll reject it. Right? Now, the problem with this approach is that in high dimensions, volume does weird things. Remember, as we go further away from the mode, we get more and more volume, right? So it turns out there's exponentially more volume on the outside of the typical set than on the inside. And this kind of warps our intuitions as to where the proposals will go. So what you really want to think about the proposals looking like is not a circle, but really something like this. Can you guys see that? Right? Most of our proposals jump on the outside of the typical set. But when we move away to the outside of the typical set, we're moving away from the mode, our density falls off so quickly, these points all get rejected. Right? The only way to maintain a reasonable acceptance probability is to shrink that size of that perturbation down to a really, really small neighborhood. right? So if we shrink it really, if we just add little bits of noise, then it doesn't really matter what the bias is, because we're still going to be within the typical set. Unfortunately, if we do that, then we're not going anywhere, right? We're exactly in the circumstance where we have this tiny little transition that's stuck to a small neighborhood around where we started. So it turns out no matter how you tune random walk metropolis, no matter how big you make that noise, you're going to be in the circumstance where you just have very inefficient exploration and very, very poor Markov chain Monte Carlo estimators. Right? So this is what we want to avoid. So if we want to be able to scale up Markov chain Monte Carlo to these high-dimensional spaces that are characteristic of wide data models, then we need a better way of exploring. Right? We need to avoid this guessing and checking. We can't afford to randomly try and check in high dimensions, because the probability of accepting one of those random guesses is going to get exponentially small. Very, very, very wasteful. What we really need is some kind of transition that knows the shape of this surface. Right? We need more information to guide us directly along the typical set. So we want something that kind of looks like this. Right? Something that can just surf across the typical set, very rapidly moving away from where we started to new unexplored regions of the typical set. Right? This is the kind of effective exploration that we need to be able to scale up MCMC to these infinite dimensional spaces. Unfortunately, this is much easier said than done, right? Because we don't know what the typical set looks like for an arbitrary problem, right? As a user, you're going to build up a big complex model to incorporate all of those systematic effects in your data. That's going to lead to a really complicated typical set, right? Now, as a statistician, I'm not going to know how to engineer a solution to tackle that particular problem. So we need to figure out what information we need, right? We need to automate this process. And that really means trying to extract information about that surface in a principled way. And fortunately, that's exactly what Hamiltonian Monte Carlo does. Right, so Hamiltonian Monte Carlo is a really, really unique way of taking this typical set, taking the surface, and extracting information about it so that we know how to move along it. Now, the actual algorithm is based in a field of mathematics called differential geometry, which is very, very beautiful, but it's not the most intuitive mathematics out there. So instead of getting into any kind of detail mathematically as to how this works, I'm going to provide a cartoon that's hopefully going to build up some intuition that will help us really understand what's going on in the algorithm. And so the key to this cartoon starts with a simple typical set, right? We have our, again, cartoon of the typical set, our concentration of all probability onto the surface. And in order to move along it, remember, we need more information, right? We need something to guide us. And a very, very natural way of doing this is with a vector field. So all a vector field is the assignment of a direction to every point in space. And the important bit is that if we have this direction, then we don't have to guess anymore. Right? If I'm at some point in the typical set, I can just follow this arrow. And because it's aligned with the typical set, it tells me to jump to a new point that's also in the typical set. And then I get to that new point, and I can just do the same thing. Right? I just follow these arrows. And then what that generates is a trajectory that moves through the typical set exactly as we want it to. Now, this vector field is nice, but it's not necessarily any easier to find, right? It's just kind of changing the problem around a little bit. What's nice about vector fields is that we can construct them pretty naturally. Not necessarily this vector field, but a vector field. And we do that by looking at the density of our target function, our target distribution. Right? So if we specify our problem with this density function, so the density isn't showed in green relative to the typical set in red. You can kind of think like a Gaussian example that we saw before. Well, that's a function, right? We can take the gradient of that function. And that gradient is a vector field. It's an arrow everywhere in space. Now, it's not particularly useful for our case because it points to the mode. Right? And if we were to follow along this vector field, we'd crash into the mode and not stay in the typical set. Right? That's an optimization. That's not what we're trying to do. We want to stay around the mode. And so it's not quite what we want, but we could potentially transform it, right? We could potentially correct the gradient. There's information there. We just need to somehow twist it, to rotate it, so that we're going in the right direction. And this is what that differential geometry does, right? It provides a way of automatically correcting the gradient. Now, what's cool is that instead of going into the math, we can appeal to physics. Because the same math that we need to use also describes classical mechanics. Right? So instead of trying to think about this probabilistically, in terms of a mode and a gradient and a typical set, it turns out that mathematically this is equivalent to a physical system with a planet, a gravitational field, and an orbit. Right? The math describing these systems are exactly the same. So what's cool is now we can think about this physically and hopefully bring some intuition to it. In particular, because these are equivalent systems, if I just take a satellite and put it out into space and let it free fall in gravity, what's going to happen? Anyone? Well, it's going to be the same thing that we saw before, right? It's going to crash into the surface of the planet. Right? It's clearly a pretty catastrophic outcome. So what's missing, right? How do we get a satellite in orbit without it crashing into the surface of the planet? We're going to need an answer from the audience. Momentum, right? We're missing some transverse motion that keeps us from falling straight down. But we've got to be careful in how we do that. So imagine that we add too little momentum. Well, now we're going to delay the crash a little bit, but gravity's still too strong, right? Gravity is still too strong for us to escape. We end up crashing. If we add too much momentum, well, now we run into the opposite problem. Now gravity is not strong enough to capture us at all, and we end up flying off to infinity, right? Neither of those are what we want. So if we want to follow along the orbit, we have to very, very carefully add just the right amount of momentum, right? And if we can do that, then what do you know? The equations of motion for this physical system are exactly the vector field that we want. And the physical trajectory of our little satellite is exactly the trajectory we want to move through the typical set. Right? So the key to Hamiltonian Monte Carlo is to add these momenta and these momentum parameters in just the right way. And it turns out it's one of the unique ways of doing that. Right? This is not just some ad hoc algorithm that seems to work. It's this really, really principled reason why it works. And it's really uniquely suited to do so. Right? It's a very, very important new way of thinking about these high-dimensional problems. So let's go through a little bit more detail about how we do this operationally. Right? So the first thing that we're going to do is we're going to take our parameters Q, and we're going to expand them. We're going to add these momenta. So this is going to double the size of our space, because for every parameter, I'm going to add in a corresponding momentum. And then what I have to do is lift up our target distribution onto this bigger space. Right? I need to define some probabilistic structure to these momenta. And the way I'm going to do that is with a conditional distribution. So I start with my target distribution, and then I'm going to define a conditional distribution for the momenta, so that gives me a joint distribution over the momenta and the positions. Right? And this is a very, very important decomposition, because what it means is if I throw the momenta away, I always recover my target distribution. So I'm going to be able to lift everything up, and at the end, I can just project back down. I can just get rid of the momenta, ignore it completely, and I'm always going to be able to recover my original system. So the cartoon, it looks something like this. We'll start with our original target distribution, defined on our original space. So here, just a one-dimensional Gaussian. I'm going to lift it up to this momenta space by adding a conditional distribution for the momenta. This gives me this joint distribution. And it turns out this joint distribution has a very, very special property that allows us to automatically construct a vector field and then generate the corresponding trajectories. Right? So that's the general kind of intuition as to what we're trying to do. Now, to construct the actual Markov chain, we're going to have to do this transformation up and down from parameter space to this extended space. And so the actual transition will look something like this. We start with a Q, right? We start with some position in parameter space. We don't have any momenta because it's just a made-up auxiliary parameter. So the first thing that we have to do is add some momentum. Fortunately, we have that conditional distribution, right? So we can sample momentum given a Q. And that's going to randomly lift us up to some new point in parameter space. In this extended parameter space. Once we're on this extended parameter space, now we can follow the trajectories, right? Now we can generate this very, very efficient exploration. And then once we're done, we just throw the momenta away, right? We just project back down to our original parameter space. So when you compose those three steps together, what you get is a trajectory that moves through the typical set of the target distribution, right? So we're kind of lifting everything up to this bigger space, and it's the shadow of the motion there that's doing the exploration that we care about. Now, a little bit more detailed of how this happens, how we actually generate that vector field. The first thing we do is we start with the joint density over this extended space. Right? Remember, we start with pi of q, and we're going to define some pi of p given q. The minus log of that density gives us what's called a Hamiltonian function. Right? And so that Hamiltonian function, we can really think about as having two contributions. Right? We just take the log of the product to get the sum of the two individual terms. That first term, the minus log of this conditional distribution for the momenta, is what we call a kinetic energy, just a convenient name. And then the second term we call a potential energy. Right? So the potential energy is completely specified by our target density, and the kinetic energy is not. So the kinetic energy is a tuning parameter. Every choice of kinetic energy gives us a valid algorithm. Some might be more effective than others, but they're all going to have this kind of efficient exploration. Once we have this Hamiltonian, then we can immediately generate the vector field that we want. And these are what are called Hamilton's equations, and they just follow immediately from having that Hamiltonian function. Now, the thing you want to note here is that in that bottom equation, right? So on top we have an arrow in the parameter direction, and the bottom we have an arrow in the momentum direction, right? So together they define an arrow that we want to follow in the extended parameter space. But down there in the second arrow, you can see dv dq. Right? Remember, v is the target density, or at least the log of it. So dv dq is the gradient that we saw before. Right? So just as I argued in that cartoon, all we're doing in Hamiltonian Monte Carlo is taking the gradient, and then we're counterbalancing it with those two other terms. Here we can see they're given by the momentum. And this exactly corrects the gradient so that instead of pointing towards the mode, it points transversely to stay along the typical set. Right? So the information that we're adding here comes from the gradients, and then we have to correct it in a very special way to ensure that we get the right exploration that we want. Right? But the Hamiltonian Monte Carlo algorithm does all of that for us. Right? All we have to do is provide our model and our gradients, and the rest happens for free. So another challenge when it comes to the implementation is that we can't actually integrate these equations analytically. This is a system of ordinary differential equations, not something that we can solve analytically. However, we can numerically approximate it pretty well. Right? I'll talk in a little bit more detail about how we do this in a few minutes, but the short version is that we're going to get some really clean equations that we can implement in a few lines. And you can kind of see we get these little small steps with this step size epsilon controlling just how small we're discretizing time. These are really, really accurate, but there is some error that we introduce. Right? There's always going to be some residual error no matter how small we make that step size. And unfortunately, that error will bias our Markov chain. Right? We're not going to be getting exact samples anymore. We're not going to be exploring the typical set exactly. And that has some weird consequences. It's really hard to try to figure out how bad that biases our problem. So what we're going to do instead is treat the numerical trajectory as a proposal, just like we did in random walk metropolis. Right? So we're going to run our numerical trajectory, and then we're going to apply an acceptance procedure. So that if the numerical trajectory ends up being close to the true trajectory, then we accept it. And if it's far away from the true trajectory, then we'll reject it, go back to where we started, and have to try again. Right? It turns out this exactly corrects for any error that we've introduced with these discretized these numerical approximations to our true trajectories. So if you put this all together, this is kind of intro Hamiltonian Monte Carlo, right? This is what you'd see in Radford-Neal's review from 2011, right? This is where we were up until a few years ago. And it sounds really good because you can write this in 20 lines of R or C++ or Python or whatever language is your favorite language. This is really easy to write down. But it's not really easy to use. And the problem is that there's lots of inputs here that we don't have a strong idea of how to tune, right? For example, what's the kinetic energy? We don't really have any guidance of how to choose that. And it turns out some choices of kinetic energy lead to very, very fast performance, and some lead to very bad performance. And it's not clear how we should choose it. Then there's things like the integration time. One thing I haven't addressed at all is how long do we move along the vector field? Right? Clearly, if we just go for a short amount of time, we're not really taking advantage of these nice long trajectories. But at the same time, if we go too long, we end up coming back to where we started, and we end up getting redundant exploration that just wastes our computational resources. So there's a delicate tuning problem there, too. And then there's the step size, right? How accurate of an integrator do we need? The more accurate it is, the more expensive it will be, right? But we'll get a higher acceptance probability. On the other hand, if we make it less accurate, it's faster, but then we reject a lot, right? So we're not getting quite as effective exploration. So there's, again, some kind of delicate tuning parameter. And this was the real challenge up till a few years ago. HMC had all of these nice properties, and if you knew how to tune it to your problem, then it would work really well. But if you didn't know how to tune it, then you would just arbitrarily choose these values, you'd get terrible performance, and it wouldn't look like it was worth all of the trouble of computing gradients. Fortunately, that was a long time ago. So in the past few years, me and some of my colleagues, both on the STAN team and my colleagues in the UK, have been working on understanding this problem more. And we've really started to, by further looking into the mathematics of the problem, been able to understand how we should tune all of these parameters. In particular, how these parameters interact with your target distribution to define the overall performance. So I just want to very briefly go over some of the ideas that we've been playing with and kind of the new perspective that you want to look at this problem with, because it will help us understand some of the limitations in the overall implementation. Okay, so the first thing we have to do is kind of change the way we think about this problem. We started off by thinking about it in terms of position and momenta, right? This was kind of the way we constructed the algorithm, and hence the most natural way to think about it. But it turns out there's a better way of thinking about this problem. And to see it, let's just look at a Markov chain, right? Let's run a few transitions. So the first thing we're going to do is run one transition, where again we lift, we run along the trajectory, and then we project back down, right? Now let's do it again. We lift, we move along the trajectory, project back down, lift, move along the trajectory, right? And so hopefully you start seeing there's a pattern emerging here. There's two very, very different kinds of motion. The trajectories are actually moving on level sets of that Hamiltonian function, right? No matter how long we run that integration time, we're always only going to be able to explore this one little level set. The momentum resampling that we get by throwing the momenta away and then resampling new momenta, that gives us this random walk between the level sets themselves. So we're actually getting these two very different forms of exploration. The trajectories move along the level sets, and the momentum resampling moves us between the level sets. So we really want to think about this problem not in terms of position momenta, but rather level sets and energies that label the level sets. Right? In particular, we can take our joint distribution over P and Q and decompose it into a conditional distribution over the level sets, and then a marginal distribution that tells us which level sets are important. Right? And what's nice about this is that the trajectories determine how well we explore the level sets, and hence how well we explore that conditional distribution, and the momentum resampling informs us how well we explore the marginal energy distribution. So now we can study these two things separately. We can split the problem apart and worry just about one at a time. So the first thing we want to look at is that marginal energy distribution, because it turns out this gives us a way of understanding how to choose the kinetic energy. So for example, let's say we chose a poor kinetic energy. What that would manifest as is the marginal energy distribution being really, really wide, but the energies that we could get by resampling the momenta being really, really narrow. Right? In other words, there's lots of level sets that matter, but when we resample the momentum, we're only able to jump to very, very close level sets. Right? It takes a long, long time to be able to explore all the level sets that matter. So it doesn't matter if we can explore the level sets efficiently. If we can't see all of the level sets, then we're always going to have very large autocorrelations. Fortunately, if we can better choose the kinetic energy, we get a much, much better interaction with the target distribution, and that would give us something that looks more like this. Right? We get some momentum resampling that can jump to any level set that matters every single time. We're essentially getting exact samples from this marginal energy distribution. Now, it turns out it's kind of hard to turn this into an explicit algorithm for how to choose the kinetic energy, but we can use it to motivate how to choose families of kinetic energies, or how to optimize within a certain family. So in STAN, you might be familiar with the fact that we use these Euclidean metrics, and we optimize them to go towards the covariance of the target distribution. That can be motivated from this perspective. And we can also now use this as a diagnostic, right? So this is something that you can plot in the most recent versions of STAN, where we provide this information to you in the chain. And so you can make this plot and see whether or not you have a good kinetic energy. So this gives us some understanding of how to choose the kinetic energy. And then we can move on to choosing the integration time. Right? So we're assuming that we can explore the level sets that matter sufficiently well. And if we can do that, now what's important is choosing the integration time so that we can explore the level sets themselves in an efficient fashion. And what ends up happening on the level sets is a pretty characteristic behavior that looks like this. So as we first start moving on a new level set, right? So we've resampled the momentum, we've jumped to a new level set, and now we're moving along that level set. And initially, everything's great because we haven't seen anything on this level set before. So as we increase the integration time, we're seeing new and new points, and all of those points are really, really informative. Right? Everything's new and exciting. But eventually, we kind of move around the space once and come back close to where we started. And once we do that, we're still exploring new parts of the level set, but they're close to places we've already explored. Right? We're just kind of refining the exploration that we've already done. And so you'll notice the effective sample size is still increasing. It's just increasing at a very, very slow rate. Right? So we go from this very, very efficient superlinear regime to this very, very inefficient asymptotic regime, where we have diminished returns. Right? As we continue to waste effort, we're getting very, very little exploration back. And so we can, to see how we want to choose the integration time, let's normalize the effective sample size by the cost, which is just going to be linear with the integration time. Right? The more we integrate, the more expensive it will be. And so we divide that by cost, you can see there's a very clear bump. Right? Very clearly there's an optimal integration time that depends on where we are. Right? This is going to be different everywhere in space. But if we could identify that, then we know exactly for how long to integrate. So from this perspective, we can start understanding about how algorithms like the no U-turn sampler work. Right? It turns out the no U-turn sampler, the NUT sampler in STAN, optimizes this integration time in very simple cases. Right? Not in all cases, but in a lot of cases. So we're just now starting to understand how these things work and motivate not just why NUTS works, but also new algorithms that might be able to do better than NUTS in cases where NUTS might be having problems. Right? So this provides some intuition as to how to choose the kinetic energy and how to choose the integration time. And then what's left is how to numerically integrate these solutions. Right? We have to use this numerical integrator to approximate the exact trajectories. So again, we have our vector field that we want to follow. There's these exact trajectories that we would like to be able to follow, but we can't. And instead, we're going to rely on numerical approximations. And it turns out this is kind of a subtle problem, because if you throw it just like a standard numerical solver at this problem, it's not going to look very good. And the problem with most numerical solvers is that the errors add together coherently. So the longer you integrate, the more you drift away from the true solution. Right? There's a very, very characteristic bias away. And it turns out that the size of that drift, the size of that bias, grows with increasing dimension. And so if you're in a high-dimensional space, that drift is so strong, you're never going to be able to follow the true solution for more than an infinitesimal amount of time. Right? And that's not good, because we want to follow for very long times. Fortunately, we have these symplectic integrators that I mentioned. And these symplectic integrators, we actually derive from the mathematics of these systems themselves. They're very, very unique to these problems. And one of the magical properties of symplectic integrators is that they don't drift. We can integrate for very, very long times, even in incredibly high dimensions. Right? We're talking millions of parameters, tens of millions of parameters, no problem at all. Right? And so no matter what our problem looks like, these symplectic integrators just track near the solution. Right? They oscillate away, but then they come back. They oscillate away, then they come back. Right? So provided that we keep integrating, we'll eventually be able to get a high acceptance probability, and we'll be able to really explore the entirety of those level sets. Right? So one of the things you have to be careful about when using HMC is to use a symplectic integrator. If you don't use a symplectic integrator, you kind of lose the ability to translate the theoretical power of the algorithm into practice. But even once we've chosen these symplectic integrators, which will end up looking something like those top two equations, we have to choose the step size. Right? Again, there is this delicate tuning issue. If the step size was too big, we'd get very inaccurate solutions. They'd be cheap, they'd be fast, because we'd be making these big jumps. But then they'd have a very low acceptance probability, and most of those proposals would be wasted. So we spend all of our time trying to generate these proposals, and we still wouldn't go anywhere. On the other hand, if the step size is too small, then we get these very accurate trajectories. We accept all the time, but then we waste all of our computational effort on making these tiny, tiny, tiny little steps. Right? So we want to choose something in the middle. We want a step size that's not so big that we get large rejections, but not so small that we have very, very expensive simulations. And it turns out we can actually calculate this in a semi-analytic way by looking at how the numerical solutions relate to the true solutions. So it turns out, if you assume this is our true solution here, right? It turns out we can actually transform this into the symplectic integrator solution. So if this is our exact trajectory, we can transform it in a very, very specific way into the approximate trajectory. Right? So all of our numerical solutions lie on that outer circle. And we can bound what those little light red arrows are. Right? We can bound that transformation that we need to go from the exact to the approximate. And so by integrating over all of those little deviations, we can calculate how accurate the solution is. And we can turn that into a relationship between the cost of the algorithm and the step size. So what we end up getting are these two lines here. And so on the y-axis, we have the cost of the algorithm. And on the x-axis, we have the average acceptance probability, which is a function of the step size. Right? And it turns out that for almost all models, the relationship between these two is bounded between those two lines. Right? In particular, over here between 0.6 and 0.8, right? This is really, really, really flat. And it's near optimal. And so all we have to do is choose a step size such that the average acceptance probability is between 0.6 and 0.8, and we're done. Right? Again, in most models. We'll see some issues where this might not be the case in the second lecture. So when we put all this stuff together, we now have a lot of mathematical intuition as to how to choose the kinetic energy, how to choose the integration time, how to choose the step size. And so we can automate all of that so users don't have to worry about it. And this is the basis behind STAN. Right? So the idea in STAN is to try to decouple the two steps of inference. Remember, the two steps of inference were the modeling step, where you as the user choose a prior and a likelihood that really represents your data. And then there's the computation step, where we compute these expectations. What we really love to do is split those apart. Let you as a user build the model you want to, and then we'll use Hamiltonian Monte Carlo to automatically fit those models, at least as best as we can. And so to do that, we have tools that help every one of the stages. We have a modeling language that facilitates the building of these models. Right? We saw some examples of those models in the two previous lectures. Once you've built your model in the modeling language, you then hand it off to STAN. We take that, we turn it into C++ code. We use state-of-the-art tools like automatic differentiation to exactly get the gradients in a very, very efficient fashion. Once we have the model and the gradients, we're now ready to run HMC. And we can also then use these adaptation algorithms that will tune HMC to not just ensure that you get some performance, but you get near optimal performance. Right? So the last two steps can happen completely automatically behind the scenes. And so after STAN's done running, so you build your model, hit go in STAN, we take it, we run those two steps, we run the Markov chains, then we return to you your results. And then you can then take them to the inferences that you want. So that sounds all well and good, but I do want to end on a warning. Because MCMC doesn't always do what we want it to. Right? And so I want to kind of talk about some of the things you might want to look out for. In particular, when does Markov chain Monte Carlo go wrong? Because one of the really, really cool things about HMC is that it's not just faster. It turns out it's more robust to a lot of these pathologies. Right? So it's giving you not just faster results, but better results. And when it fails and it doesn't give us the results we want, it tells us. Right? And this is the motivation behind a lot of the new diagnostics that you're seeing pop up in STAN. Okay, so let's consider what the ideal case, right? What happens when MCMC is working perfectly? Well, when everything is good, we get 3 stages of every Markov chain. And the first stage is convergence, right? This is when we start somewhere away from the typical set and we converge into the typical set. Right? This is nominally what warm-up is for. And so you can see on the right-hand side, we have the accuracy of an expectation. And you can see it begins, nothing really good happens, right? Because we haven't hit any of the regions of high probability. But once we've hit the typical set, now we get our first sampling stage. And the first sampling stage is when we've gone over the typical set once. Right? So we've kind of just laid off the groundwork of where the typical set is. Once we've done that, these expectations get really, really good. And then as we continue to go around the typical set over and over and over and over again, we get this 1 over square root of n improvement in our expectations. Right? This is kind of the expected asymptotic performance. So we get this very, very big improvement and then this slow increase. Now, when everything's working, we can actually calculate what's happening in that tail. Right? We can calculate how far away we are, or at least we can estimate it. And that provides us a really, really nice understanding of how close our expectation, our approximate expectation is. Right? How long do we need to keep running? Right? How many effective samples do we have? Right? That's all things we can do in this ideal case. But we can't always do this, right? Because for this to work, we need to have a nice, simple, typical set. And unfortunately, not all typical sets look like this. You can imagine having a typical set that looks something like this. Most of it looks really good, but there's this little region down here in the bottom. Right? There's this region of high curvature. And the problem is that a lot of Markov transitions don't have the resolution to get into that little crack. Right? So what's going to happen is the Markov chains is going to get close to it, and they're just going to bounce right past it. Right? It's going to miss that whole region of high probability because the step size is just going to be too big. So the probability of being able to just wedge in there is just going to be too small. So what's going to happen is that we're going to get biased expectations, right? Because we're only going to have partial exploration. At least that's what we would think. It turns out something weird happens because the Markov chain has to get the right answer asymptotically. Right? Remember, even though the Markov chain can't get into that little region, with an infinite number of iterations, it has to be able to calculate the right expectation. So how does it do that? Well, it does it in a really cool way. So initially, as we're trying to explore this pathological typical set, everything looks good. Right? Our Markov chain is able to go through these nice regions, no problem. But eventually, we're going to get close to that pathological region. And when we get close enough, the Markov chain sticks. Right? Has anybody ever run a Markov chain and seen this before? Okay, good for you. This happens a lot when you're trying to fit things like hierarchical models in bugs. And it's indicative that there's this really, really nasty pathology going on. So what's happening here is that because the Markov chain can't get into that little crack, it's going to get stuck. And as it gets stuck, as it stays there, it draws the expectations down as if it were actually exploring that region. Right? Now, eventually, it's going to overcompensate, and the expectations are going to swing too small. So in order to get rid of that, or to correct for that, it then releases and then continues to explore. So what ends up happening is that our expectations don't converge in this nice way. They oscillate. They get too big, and then they get too small, and then they get too big, and then they get too small. And if you cut this off for any finite time, you get a bias. And that bias can be really, really big. So the thing theoretically that we have to worry about here is what's called geometric ergodicity. It's basically the minimal condition necessary to ensure that we have this nice behavior, that we don't have one of these weird pathologies. And what it really guarantees is what's called the Markov chain Monte Carlo central limit theorem. Right? This is what we kind of talk about in STAN and most MCMC tools. We say that the Markov chain Monte Carlo estimators are unbiased estimators of these expectations, and the uncertainty, the variance, is given by the true variance divided by the effective sample size. Right? This is what was always quoted, but it doesn't always hold. For this to hold, we need to have this nice idealized behavior. We can't have any of those pathologies. And this is the danger with MCMC. Because if you can always calculate that number, but we don't always know whether or not it's valid. Right? We don't know if we can trust it or not. And this is where the robustness of HMC comes in. Because when HMC hits one of these bad regions, it doesn't just move past it. Right? It doesn't just ignore it. It goes crazy. It turns out that these numerical trajectories bounce off the pathological region. And it doesn't just bounce off in some small neighborhood. It bounces off to infinity really, really quickly. This is very, very easy behavior for us to diagnose automatically. So this is what we call a divergence. Right? This is, if you run RSTAN, you should get, every now and then you get some warning that says, stop, you saw some divergences, don't go. Right? What's happening is that the Markov chain, the transition, has gotten into a point in the typical set where there's really, really bad neighborhood. It's flown off to infinity, and we've caught it and seen that something's wrong. Right? So if you're a user of RSTAN, this is how that would manifest. Right? After you've run your chain, you'll see that there's this warning about divergent transitions and some suggestion as to how to change the average acceptance probability. And the idea there is that if you make the step size smaller, you might be able to get a little bit closer in that region. But oftentimes, no step size is going to work. You have to consider changing your model, either re-implementing it in a different way or changing your priors or somehow tweaking things around. And we'll see how this manifests in a real example in the next lecture. Okay. So I'll nominally end there. We'll show one more slide after this to go into Kentaro's talk. But let's just kind of review what we've done, right? We've motivated that we want to deal with these wide data problems. We want to be able to build models that can capture really, really nasty structure and the data sets that we're collecting that really is going to allow us to extract as much information as possible. And to do that with Bayesian inference, it means we have to compute high-dimensional integrals, right? And high-dimensional integrals mean we need to find the typical set. MCMC has, theoretically gets there, does that exploration in an infinite amount of time. But to do that in a finite amount of time, in these high-dimensional problems, we need tools like Hamiltonian Monte Carlo, right? We need this very, very effective exploration. And that's hard to do, right? So if you're really, really careful in how we implement the algorithm, we have to be careful to respect all the mathematics behind it. But fortunately, Stan does that for you, right? So when you run Stan, we kind of use the state-of-the-art understanding to really tune this as well as possible. And then when things go wrong, we'll tell you, right? We'll give you these diagnostics so you have some idea of how things are going. So before getting to questions, I just want to show something that we're working on recently. Sorry. Right. So Kentaro talked about doing parallel tempering with Stan. And the idea with parallel tempering, right, there we go. Okay. You have a multimodal distribution, and what this means is your typical sets are disconnected, right? So you can explore one of these typical sets, but you can't jump between them. And this is the challenge. And so there's lots of algorithms out there that take this kind of thermodynamic idea into account. So what we're going to do is we're going to take our target distribution, our multimodal complicated target distribution, and we're going to complement it with some simple unimodal distribution. And we want to interpolate between the two. So in Kentaro's case, he was taking a uniform distribution, and then the complicated posterior distribution on the other side, and then you have this interpolation given by an inverse temperature. Right? So in Kentaro's case, as the temperature got big, you got closer to the uniform. In this case, when beta gets small, you get closer to that uniform. Right? And the real challenge with this is trying to choose a partition efficiently. Because the ability to move between these two distributions depends on how well this partition matches the kind of shape of the interpolation. And it's really hard to identify what the optimal partition is. Right? So Kentaro did this geometric partition, which in some cases works okay, but in really, really hard problems, you get these phase transitions. And it's really, really hard to kind of figure out where this partition should be dense and where it should be sparse. And so what this manifests as is something like parallel tempering will work if you run long enough, but you can run into issues where it takes a long time to transition back to t equals 1. And you saw that a little bit in his plots, right? There was a lot of transitions between the top 4 replicates, but there weren't as many going from t equals 2 to t equals 1, right? And that's the real challenge. So simulated annealing, simulated tempering, parallel tempering, they all run into the issue that it's hard to choose this partition. So it turns out you can generalize Hamiltonian Monte Carlo. You can make that beta a dynamic variable, and the math will figure out what the partition is for you. So what we end up getting are these trajectories that move not just through momentum and position space, but position, momentum, and temperature space. Right? So we're going to start at that base distribution. In this case, I'm going to say we have a unimodal Gaussian. And then we run this adiabatic Monte Carlo algorithm. And it generates these trajectories that start changing the temperature dynamically as well. And it turns out it changes the temperature in a mathematically optimal way. Right? So this is kind of the next generation of Hamiltonian Monte Carlo. We take a little bit more advanced mathematics, and it allows us to tackle even harder problems. This won't be in Stan anytime soon. There's still some mathematical issues we're dealing with, and tuning is going to be really, really hard. But theoretically, we're going to be able to get there. So we can have these nice implementations like Kentaro's working on that will help us deal with it now, but eventually, hopefully, Stan will be there to have a replacement in the future. Cool. All right, so I guess take some questions in case anything wasn't clear.
The description I read in a book for HMC was assuming a normal distribution for resampling P.
Yeah.
And do you mean Stan does better or something different?
Yeah, so take a second for the slides to get back. There we go. Ugh. There we go. Okay, yeah. So there's a question of how to choose kinetic energy. And in Radford's paper, and this was something that actually got me interested in Hamiltonian Monte Carlo, you just assume that T is 1/2 p squared, which corresponds to having a Gaussian conditional distribution. There's no reason why that has to be, right? You can imagine playing with a lot of other things. Now, it turns out there's a lot of theoretical analysis that shows that a Gaussian is near optimal. If you go too heavy in momentum, you get these really large momentas, but then you never quite get back. So you end up going too far in the tails. If you have too light momentum, if you have a very kind of narrow distribution, then you don't go far enough. So there is something special about the Gaussian, but you could theoretically play with other things. The big question is not so much the form of that, but rather what covariance do you choose? Right? Do you choose a covariance that's diagonal, that's dense? Is it just unit? Is it just uniform along the diagonal? Or does it change with position? Right? So there's two directions when choosing the kinetic energy. There's the form of the density. Whether is it Gaussian, is it Laplace, is it student T, is it something heavy-tailed? And then orthogonal to that is the choice of covariance. So you have these two choices to make. So in Stan, we stick to the Gaussian, right? We because it has some nice properties, we use that for now. It's easy for us to change it. We just haven't found a nice empirical reason as to why. And then we have various choices of the covariance. So in command Stan and R Stan, the option is the metric. And the metric can be unit E, which is just a diagonal one, diag E, which is a diagonal covariance matrix, or dense E. And in the most recent version of the development version of Stan, there's now Riemannian HMC, which allows us to have a kind of a dynamic covariance that changes depending on where you are in parameter space. So long answer to your very, very short question. We theoretically could, because the other choices of the shape of the kinetic energy don't seem to work very well, we haven't exposed it. But if for any reason you want to try it, or you think there's some other reason to try that, we can talk about trying to expose it.
Thank you.
It can't have been that clear. Okay. So we'll take like a 10-minute break? Okay, cool. And if you have any questions, I'm happy to answer them during the break. When we come back, we're going to deal with some explicit models. So we'll get into the Stan modeling language, and we'll talk about how we actually use HMC to do some cool sampling. All right, thanks, guys.